Hi everybody, and welcome back to Geology 311, Stratigraphy and Basin Analysis. This week, which is week 7, we are going to be looking at chapters 8 and 9 in the Brookfield text, which focus on stratigraphic systems and basin analysis. If you haven't already gotten in the habit of printing off the course notes for this one and following along with the lectures, I strongly encourage you to do so for this week's lecture series. This stuff can get a little bit abstract. So I want to make sure everybody paces themselves through it, but not to get too intimidated if that wasn't already kind of a foreboding warning. Anyway, let's jump right in. To start out, we're going to be looking at cyclic successions. These are defined as any strata or series of strata that show repeating patterns that can be related to depositional processes and specific environmental conditions at the time that these series were being deposited. Think of this as cyclic sedimentation. And the cyclothems that we looked at in Project 2 and that we see throughout the Pennsylvanian systems are a good example of these. You have a series of different depositional environments that reflect a change, in this case, in sea level and climate. And they repeat. So you have a package of transgressive and regressive sequences, and they keep repeating. So that's what we mean by cyclic successions. The result of these types of series is you get these vertical successions that show that repetitive arrangement over and over again. And we can start interpreting those to see what kind of timescales they represent. But it's important to note that not all of these cyclic successions operate on the same type of timescales. Before we get into what different types of timescales we have, though, we should really look at the mechanisms behind these cyclic sedimentary or stratigraphic successions. First off are what we call autocyclic successions. These are going to be a series of repeating stratigraphic patterns that are controlled by processes that are going on within the depositional basin itself. Not to be confused with allocyclic successions, which happen from outside of the basin. Now, our autocyclic successions, I kind of skipped ahead a little bit, but these are going to show very limited stratigraphic continuity because they're only happening within one basin. So this isn't a signal that you're going to see throughout an entire continent. You're just going to see it maybe in one basin to itself. So these would be things like storm beds that aren't cyclic or periodic, or turbidites, for example, things that do happen to some degree of repeating or cyclicity, but they're only going to be occurring in that particular basin or environment. Meanwhile, our allocyclic successions are external to the depositional basin. So these are caused by something outside of the basin. These are much more climate and tectonically controlled. So think of autocyclic is going to be unique to a given basin. It takes place within it. Allocyclic successions are going to be caused and controlled by things happening outside of the basin, so thus it's something that you can potentially see in lots of different sedimentary basins. So these are over much longer distances and in many cases multiple basins. This would be something like variation of climate that is showing a sea level change. So large-scale global glaciations, the kind of glacial, interglacial cycles we saw during the Pleistocene, but even the Ordovician would be an example of this, or any type of tectonic influence on sediment supply. So the uplift of the Appalachian Mountains in the Paleozoic era, for example, affected numerous basins. It infected climate and definitely affected sediment supply. That's going to be more of an allocyclic succession. To look a little bit more at what we see with allocyclic successions, we call these our first order cycles. These are very, very long-term and usually involve eustatic changes in sea level. So in other words, these are due to climate and they are changing the volume of water in an ocean. Think of it that way. This is not necessarily tectonically related. It is more eustatically controlling from climate. So a rise and fall in global sea level. would be a first order cycle. These are happening on scales between 200 and 500 million years to go from one extreme to the other and back again for a full cycle. You aren't going to see these in outcrops. Again, these represent between 200 and 500 million years worth of depositional time. So you're not going to see these in a single road cut. This is postulated to, for example, develop as Pangea was coming together, like another supercontinents. So this is due to those types of climate ramifications from building massive supercontinents. For example, seafloor spreading and then the later breakup of these supercontinents. These are happening on those types of time scales where they are having a huge impact on climate, either with seafloor spreading and how we distribute climate around the planet, or even the collision and the formation of those continents in the first place, producing mountain ranges that can also affect climate. So here we're looking at a couple of different types of allocyclic successions, and we're going to be focusing here on our first orders. So again, this is looking at geological time over about 550 million years. And you can see areas where we have relatively higher versus lower sea level throughout the Phanerozoic. So essentially the last 500 to 550 million years. You can see that in the going from the Cambrian to the Ordovician, we start seeing these massive increases in sea level. Also, this is around the time we're producing lots and lots of ocean crust. And then sea level starts to dip down towards the end of the Paleozoic, around 250 million years ago, hitting kind of the lower point that it's been in the Phanerozoic. And then it starts to build back up again later on in the Mesozoic, going into the early Cenozoic, and of course dropping during the last glacial ice age in the Holocene and the Quaternary. So first order cycles and climate states. With these highs and lows, we can actually build what we call climate states and what we call greenhouse or icehouse worlds. An icehouse state are cool periods with very low amounts of atmospheric carbon dioxide. Greenhouse states, obviously the opposite. This is warm periods with higher amounts of CO2. And again, looking at the diagram to the right, you can see that when we have relatively high or low sea level, what is the mean global average for temperature, and see how that changes with bands of our greenhouse and our icehouse states. Notice they don't exactly match up perfectly with what we call as our climate modes. We're warm and cool because you have transitions. An icehouse state starts out, or it starts out warm, it gets cool, and then it starts to warm up again as you go out of that into the next one. So in the latest part of the Precambrian, going through the Phanerozoic, for example, we have 3 icehouse states and 2 greenhouse states. So make sure I got my pen turned on here. Our icehouse states are going to be in the very end of the Precambrian, going into the Cambrian. We have another one in the Carboniferous throughout the Permo-Triassic. Again, this is a time of lowering sea levels and some glacial advancements. And then we start, of course, seeing one in the Cenozoic. Meanwhile, our greenhouse worlds are happening in the Ordovician, Silurian, going into the Devonian, and again throughout most of the Mesozoic era. Furthermore, sea level and moisture conditions are obviously going to be influenced by climate. So how much rainfall you're getting and what the average sea level is it ultimately high or ultimately low? This is based on climate, and climate is strongly influenced by tectonics, the location of continents and how we distribute temperatures around the planet. So for example, the Triassic through the Jurassic and the Devonian are very dry and very warm. The Carboniferous through the Permian is wet and cool, but it's still a time when we're starting to see these fluctuations in sea level. And of course, there's other things like orbital parameters, carbon dioxide levels, how much tectonic and volcanism you have going on that's going to be affecting climate as well. But I just wanted to show here how there is definitely a relationship between sea level, average global temperature, or mean global temperature, and these types of climate modes and what we call our climate states, our icehouse and greenhouse worlds, and how those correspond with glaciations. Now, what about our second order cycles? These are going to be happening on a duration of tens to hundreds of millions of years. So they are still very large spans of time, but these are something we can trace a little bit more easier than our first order cycles. They're still macro scale and usually too large to see in a single outcrop, though you can see them in probably one day's worth of driving around and looking at various outcrops. These seem to be linked to considerable changes in ocean volume. So volume changes in seafloor spreading centers and sea level. So this is about how our ocean basins are changing shape. And this, of course, is done mostly by divergent plate activity. In 1963, Sloss defined what he called second order cycles or stratigraphic cycles for North America, and we call these the Sloss megasequences. And these include the Sauk, Tippecanoe, Kaskaskia, Absaroka, Zuni, and Tejas in order from oldest to youngest. The Sauk really begins around the Vendian period of the Proterozoic. It's the very end of the Precambrian, so maybe 600 to 650 million years ago. And the Sauk continues into the early Paleozoic, into the Ordovician, where then the Tippecanoe takes over. And then we have the Kaskaskia going on throughout, briefly in the mid to late Paleozoic. The Absaroka is late Paleozoic throughout early Mesozoic. The Zuni is late Mesozoic, and then the Tejas is Cenozoic. In between each of these, you have considerable unconformities or regressions. And that's really what these sequences are showing, is the distribution of conformable packages of sediments associated with the North American craton. And he had, by 1979, also noticed very similar cycles on other continents. So it's not something that is unique to just North America. So here's our second order supercycles or megasequences. Again, you can see how these do correspond again to some of our climate states, our icehouse state, greenhouse state. You can see that from the Precambrian through the Cambrian, the Sauk sea rises, and then in the Ordovician we drop it down. We start building it up again in the Tippecanoe throughout the Silurian, and then we drop it back down again with the Kaskaskia. Starts to once again start another transgression from the Devonian through the Mississippian. The Pennsylvanian begins with a drop in sea level, and that ends the Kaskaskia. The Absaroka is a little weird. The Absaroka sequence is considerable in size, but notice it doesn't really represent a huge package of sediment. More, this is Pangea coming together, and then we end the Absaroka with the beginning of the rifting that goes on in the Triassic. So the Zuni sequence is a major transgression, one of the biggest we've seen since the Sauk. That goes from the Jurassic through the Cretaceous period. It starts to go down a little bit in the latest Cretaceous as continents continue to disperse. And then we have kind of our current sequence with the Tejas. So I want to play this video a bit and show you kind of what's going on with these sequences. Before I hit play though, notice where on the part of the diagram here on the left where we have our Sauk sequence, Tippecanoe, Kaskaskia, Absaroka, Zuni, and Tejas. Essentially what you're looking at throughout the entire left side here, this is the sediment sequences deposited on the North American craton during the last 550 million years. Now, the Sauk sequence, you can see from left to right, starts to encroach upon the continent, and what we have is hiatus in between. That means this is areas where we don't have a Sauk, in other words, Cambrian sedimentary record. But by the time we get into the Ordovician, you're going to see that the Sauk sequence pretty much inundates the entire continent. So I'll go ahead and hit play. Okay, so you can see with both the animation and the bar that's moving up, more of North America is becoming inundated. And by the time we get pretty close here to the end of the Cambrian, most of the North American craton is underwater. And then we have a regression, and we start building it up again into the Tippecanoe sequence during the Ordovician, continuing up, and then we end that sequence, and we then go into another hiatus, and now the Kaskaskia in the Devonian starts encroaching. So this is where we would expect to find Devonian and ultimately Carboniferous sediments encroaching more and more. Sea levels are getting higher. They are now at a high for the Kaskaskia sequence. We drop them back down, ending the Kaskaskia and now starting the Absaroka sequence. This sequence starts to continue, but notice we actually see a little bit of a regression going on here, again, because we're seeing desertification during the late part of the Paleozoic going into the Mesozoic. And we finally end the Absaroka sequence around the end of the Triassic. And we have a hiatus then during the Jurassic period. Around the middle of it, we start once again building up the Zuni sequence. Sea levels getting higher again, except more on the western side, where the Western Interior Seaway is. As this continues to form, now we're seeing pole to Gulf of Mexico connection, or near close full connection. There it is. And now regression at the end of the Cretaceous, and a little bit of a transgression for the Tejas sequence in the Cenozoic. So ideally, if you go to the continental margins of the North American craton, you'll see mostly conformable sequences. Here in the Midwest, we have some Cambrian and Ordovician. We have some Devonian in some places around the Midwest. We have a little bit of Carboniferous. We had more Permian Triassic. We didn't really have much for Permian Triassic or Jurassic deposits in the mid-continent, but we do on the coasts. There is some Cretaceous deposits in the Midwest when you look at the high plains. So pretty much wherever you have, looking at this sequence diagram, wherever you have the brown, that's where you're missing sediment for that period of time. When you look at the margins, you'll see that we have a much more complete record, and that is what we see along the continental margins themselves. And we do have other order cycles. We have third, fourth, and fifth order, among others. A third order cycle is going to have an episodic rate of 1 to 10 million years. You can see these in observations in the field. You can clearly see this in a single outcrop. These are going to be caused by continental ice fluctuations or ridge changes. So these are things that are going to be deposited on a much smaller scale. A fourth order cycle has about 200,000 to about a 500,000 million, a 0.2 to 0.5 million year duration. These include some of our glaciostatic Milankovitch cycles. A lot of this is from astronomical forcing, so it's what's going on outside of our planet. A fifth order cycle, again, very, very short time scales, 0.01 to 0.2 million years. More of our other Milankovitch cycles and more other forms of astronomical forcing. So when we really get into Milankovitch cyclicity, those are more fourth and fifth order cycles. What we're seeing with our first and second order, though, are continental scale intrabasinal changes that we can see in repeating cycles, such as the Sloss sequences. Now, I'd like to switch gears a little bit here for a moment, because while we are talking about cycles, it's important that we also talk about what we call sequence stratigraphy. And a lot of sequence stratigraphy is done from seismic methods, but definitely not all of it. You can actually identify sedimentary sequences in a series of large-scale outcrops. Of course, it does make it easier with seismic sections if you know how to read seismic sections. And I know we talked a little bit about this before, but I figured I'd kind of do another quick review or actually go into a little bit more detail this time. And then we'll get into our final topic for this week, which is sequence stratigraphy. So seismic stratigraphy is any time that we are extracting stratigraphic information exclusively from seismic data. So we've already learned to read well log data. So like electrical logs taken from drill sites. This is utilizing those non-invasive methods where we make a loud vibration, maybe with an explosion or just making a lot of noise or sonar, and then getting the signal to bounce back to indicate changes in density with depth. Alternatively, sequence stratigraphy is looking at true sedimentary sequences. Now, this originally was kind of an outgrowth from seismic stratigraphy, but since then, sedimentary sequences have been identified, like I said, in rocks themselves, so we don't have to only rely on seismic methods. So what is a sedimentary sequence, though? We're going to get into more of this here in a bit, but just to give you a preview, this is any stratigraphic unit that is conformed from a conformable succession, or we would say relatively conformable. Again, remember, conformable, opposite of unconformity, meaning more or less continuous. Succession of strata that we call genetically related, meaning that it's all part of the same series of processes. But these are going to be bound above and below by unconformities or correlative conformities, things that we can make direct comparisons to. A sequence itself is one cycle of deposition that's going to be bound by a surface of erosion, non-marine erosion, and then with depositing of one significant rise and fall of sea level, one full cycle. Okay, so sea level change, going from low to high, back down to low again. That's one sequence. Now, to get the information that initially gave birth to sequence stratigraphy, again, use seismic methods. And going back to the very basic principles of how do seismic waves work, we have S waves and P waves. P waves are compressional. Think of a slinky being extended and then let go, kind of that worm-like motion of particle movement, versus an S wave, which is a shear wave, which moves back and forth as it propagates forward. So there's a zigzag as it propagates forward. Here's actually a way of looking at it in animation. Okay. So our P waves propagate forward. Our S waves propagate forward, but from a transverse motion. P waves are primary, S waves are secondary. P waves are the fastest and the first ones. S waves can be stopped by different densities. For example, P waves work great in water, S waves don't. So we send out our seismic array and we get a printout back. And as I want to remind you once again, you are not looking at depth. This is actually travel time in seconds. Distance can still be measured, but we're not doing this in terms of depth. So you're not looking at rock layers. They really do look like sedimentary units, but you're not looking at rock layers. You're looking at what we call seismic reflectors. And we've already talked a bit about the types of corrections that are needed to actually process these. But I want to talk a little more about these reflectors, these lines, which simply indicate that something is changing, that there's some kind of change. We can't look at a seismic reflector and know what kind of rock it is, but we know that there's some kind of change in the signal that bounced back our initial signal that was sent to the rock. So I went ahead and just copied this from a different textbook because I think it would be helpful to have as a graphic, but looking at the parameters that we commonly use for seismic reflections. A reflection configuration is used for interpreting bedding planes, sometimes depositional processes, again by looking at bedding planes and sometimes the sediment or stratigraphic architecture. It can tell us if there's been erosion, tell us about the subsurface, what we call paleotopography, and can also tell us about fluid contacts, again, because S and P waves move differently through different materials. We also pay attention to how continuous our reflectors are. This helps us get an idea of bedding continuity, and again, depositional processes. We look at the amplitude of the reflectors. This is going to be usually based on the speed of that signal, so velocity versus density contrast. We can get an idea of the spacing between some of our beds, and more info for fluid contact, which we see with a lot of these. Also with flexion frequency and our internal velocity. So in other words, how quickly the signal is bounced back versus how kind of it bounces around before being sent back up again. This is going to tell us about lithology a little bit. We can get an estimate from lithology, but not a lot, and a little bit about porosity. And sometimes there are external and areal associations. So what's the major depositional environment, and what's the source, and what's the geologic setting? So we can get quite a lot of information from seismic reflectors. We just need to learn how to read them first. So the configuration, remember, this is going to be the gross patterns, the stratigraphic patterns that we see on our record. So these are schematic diagrams of seismic reflections. So if you have a pattern that is what we would call parallel or subparallel, in other words, your seismic reflectors are more or less parallel to each other, this would indicate that you had sediment of some kind or another that was deposited at a more or less uniform rate. So what kind of environment would that be? Well, maybe a stable basin or a shelf that's slowly and uniformly subsiding. It's very common to find what we call divergent reflectors. In other words, they kind of branch out like an array. This shows more lateral variations in rates of deposition, just like we would for sediments, though you're not looking at sediments. And then we also see examples of prograding, both parallel and kind of a sigmoid oblique, a stacking pattern that we can see, what we call a prograding reflection configuration or a prograding pattern. And these indicate strata that are being kind of outboard building from progradation. So as sediment is going into a basin and the sediment supply is greater than the space the basin can accommodate, you get this outboard stacking of progradation. Occasionally you get deformed or chaotic reflectors, and that simply means that the sediment's very soft and it's possibly already been deformed, or it's just a high energy environment. If there's no stratal pattern and it's just chaotic in general, that could be bedrock. That could also just be disordered arrangement of any of those reflecting surfaces. They're just getting bounced all over the place. And if there's no reflection, that means we're looking at pretty much seismically homogeneous strata. So an igneous rock, a salt deposit, or if the strata are really, really steeply dipping, it's not going to send that signal back, so you get no reflection. Continuity. So how long can we trace these reflectors? Again, this is density velocity contrast, so we have laterally continuous reflectors. Discontinuous reflectors, what we call top discordant or base discordant. So a top discordant could be something like an angular unconformity. Base discordant could be outboard again stacking on some kind of a bedrock. This is really closely associated with stratal continuity. So if your reflectors are continuous, your strata likely are too. So it can tell us more information about what kind of environment we're looking at and what kind of processes were involved in depositing these. Now we get into actual sequence stratigraphy, the real beast that we're going to tackle here. This is strongly influenced, your stratigraphic sequences are strongly influenced by three main things: accommodation space, subsidence, and eustacy, or eustatic sea level. As eustatic sea level goes up and down, remember that is the amount of water in the basin, so that can be climate related. Your subsidence or uplift rate, which is tectonic, isostatic relationships with sea level, can also fluctuate. And together then you have that with accommodation space. This is the distance between the base of your basin and the surface of the sea. How much space can you actually fit sediment into? And this changes with changes in tectonics, or with isostasy and with eustacy. So as these change, as they go from one extreme to the other, especially with eustatic levels and our major cycles of sea level change, we are going to see stratigraphic evidence of those changes. And it's not just as simply as transgression regression. This is all based on the idea that our successions of stratigraphic materials and sedimentary rocks can be divided into these unconformity bound units. And these happen during single full cycles of sea level. Ultimately, the goal here is to put these units into a somewhat predictable framework of like time-rock relationships, so chronostratigraphic framework, by showing how they're formed in relation to accommodation space. And this is going to usher in what we'll be talking about after spring break, where we're really looking at the role of tectonics and the role of climate in the productions and evolution of basins. So this is why we're getting this under our belt first. So, sequence stratigraphy involves looking at depositional sequences. A depositional sequence is defined as genetically related strata bound by surfaces of erosion or non-deposition of their correlative conformities. So it's a package of strata with unconformities above and below. These depositional sequences include a couple of moving parts, and we're going to be discussing these. Depositional systems that actually produce those sediments. Parasequences, which are packages of sedimentary rock that indicate particular environments over time. Parasequence sets, which are how parasequences are stacked over time and space. System tracts, which are collections of parasequence sets and facies. And flooding surfaces, which indicate the relative placement of some of our sequence boundaries. I know this is a lot of vocab, but we're going to go through these step by step. A depositional system is any three-dimensional assemblage of lithofacies that are linked by either modern or inferred, so active or ancient processes and environments. Think of this as a fluvial, a deltaic, or a barrier island depositional system. Each of these has a lot of different parts to them. A fluvial system, you could be looking at the channel sand, you could be looking at the gravel bar, you could see the point bar, the floodplain, crevasse splay. Deltaic environments have a wide variety of sub-environments. So these are depositional systems. A fluvial system, a deltaic system. So three-dimensional assemblage of all of the rock facies that are linked to these processes and environments. That's what makes up a depositional sequence, are these systems. We're looking at the evolution of systems over time and space. So let's talk a bit about parasequences and parasequence sets, because these are the components that make up our system tracts. A parasequence is defined as relatively conformable successions of genetically related beds or bed sets bounded by marine flooding surfaces and their correlative surfaces. Okay, one part at a time. Relatively conformable. That means that this parasequence could contain some minor interruptions. We call them diastems. But there's no substantial periods of erosion or non-deposition. These are conformable. They're not missing millions and millions of years. Okay, so relatively conformable succession of genetically related beds. Well, genetically, we're talking about sediments. What we mean by that is all of the facies in a parasequence are going to be deposited laterally with one another. So in other words, as bound by Walter's law, related that way. So beds or bed sets bound by marine flooding surfaces. That's going to be a really sharp contact. That's going to indicate a separation from your shallow water facies below and your deeper water facies above. This is the really important part of the definition of a parasequence, is the presence of a marine flooding surface. It indicates that you have a significant separation, a contact from shallow water and deep water facies. So These usually have some additional characteristics, not part of the definition, not really required, but I want to go through some of the examples that you might see. Most parasequences are going to be asymmetrical in shallowing upward cycles. In other words, you're not going to see a fining upward, then a coarsening upward, a full thing, because you are going to have changes in how much sediment is being stacked. So your shallow upward portion is usually going to be thicker than the deep upward portion. Okay. It's just a common thing that you see, but not always. Also, a lot of our parasequences tend to be a few meters to maybe tens of meters thick. So these can be easily identifiable, even in outcrop and in road cut. Well, what about the relationship of parasequences and facies? These are going to be developed. Your facies are going to be developed in a parasequence with a pretty predictable vertical order based on what we can see happening today. And this is where, if you did pick up that facies model book, it could be very useful for other examples. But let's start with a couple examples. I want to look at Soliciclastic wave-dominated coasts. So those types of environments we talked about for exam 1. There are 4 facies that are commonly presented in a fixed vertical order when you are interpreting a wave-dominated coast. So here's a schematic of one of these parasequence facies models. A parasequence of a wave-dominated coast, or Soliciclastic wave-dominated coast, is going to span all of these facies. You're going to start out with a bioturbated offshore mudstone towards the bottom. Okay, so this is offshore. And then, as you go up that parasequence section, you're going to pass through storm beds from what we call the lower shore face. This is where storms can actually still have an impact on sediments. We continue then through cross-bedded upper shore face, cross-stratified sandstones. And then we pass upward from that into our seaward inclined laminae on the foreshore. So you can see in the schematic how they're kind of leaning towards offshore. And then we have a flooding surface, and we start it all over again with offshore. So this is one parasequence. It's one package of all of these facies that are showing you go from offshore to lower shore face, upper shore face, foreshore, and then we start all over again. At the very top, you're going to get this, what we call sometimes the backshore, or a coastal plain coal bed if you have a lot of organic material. And this is kind of your base that you'll start the entire thing over with. So let's look at this in a real-world example. This is an image of a parasequence that is from the Cretaceous Blackhawk Formation in Helper, Utah, very close to Price, Utah. Beautiful place. And we're looking at a wave-dominated coastline from the Middle Cretaceous. You can see there's a repeating sequence. The shore face at the bottom and the shore face at the top. Very similar looking rocks. You've got that offshore transition, which is our offshore to lower shore face. You've got the shore face then where we get into a blockier sandstone. That's that trough cross-stratified sandstones going into the foreshore where, if you look at those closely, there are leaning. You go from more thin proximal storm beds with some mudstones interbedded, and there are a lot of coals in this area too. This is actually a big coal mining area. And then your foreshore going up, flooding surface, and you start the new shore face. I do want to make a note that a single parasequence may not have all of these facies, but it still works in that predictable order from Walter's law. They're still genetically related and conformable. Now, let's look at another example, in this case, a muddy Soliciclastic shoreline. So here's our schematic for it, our model. A muddy shoreline parasequence, Soliciclastic mud-based shoreline, you'd start out with cross-bedded subtidal sands, kind of sigmoidal cross-bedded sandstones. That's going to continue upward with interbedded mudstones that are going to show a lot of bioturbation because you're at the intertidal flat. So a lot of ripple sands and crossbeds and interbeds with those bioturbated muds. That passes up into really, really bioturbated environments. And ultimately you end up with mudstones with lots of coal, part of the supertidal environment. And here's another example. This is from the Juniata Formation in Germany Valley, West Virginia, which is Ordovician in age. So tidal flat parasequences and the flooding surfaces. Now, I have a note about flooding surfaces. The flooding surfaces that we see that define our top and our bottom of the parasequences are going to be abrupt. But they're going to be representing relatively deeper water facies right on top of shallow water facies. Okay. The rocks that are above and below a flooding surface will commonly represent some non-adjacent facies. So, for example, it might be an offshore shale that's going to be sitting on top of foreshore sands. Or maybe you have shales from a prodelta right on top of a distributary mouthbar sandstone. In other words, we're skipping environments. So these may not follow Walter's law in some cases. So that's one of the important things to note about flooding surfaces, is that they may not represent Walter's law. They may not kind of correspond with those, but the units within usually do. But because we have these abrupt flooding surface contacts, you've actually maybe stripped away or you've skipped some of those other parts of the parasequences. When we stack these together, we get what's called a parasequence set. And we're going to use the basics of shore face, offshore transition to offshore as ways of describing these. And I want you to keep in mind what we were talking about with seismic reflectors and how continuous or discordant they were, and whether they were horizontal and parallel to subparallel, or whether they were discordant. A retrograde parasequence set, or parasequence stack, is a parasequence that's going to advance in a landward direction. So that's retrograding. So if we look at our example for retrogradational parasequences, it starts out with 1 and follow that shore face. That's your shoreline, in other words. And notice how it moves in the landward direction. So your facies are going to be moving that way. Kind of your typical transgression, what we usually model for a transgression. Now, the aggradational parasequence, this is going to be built vertically. What does this imply? There's really no lateral motion. This is going to be pretty much the sediments are being accumulated in junction and in tandem with changes in the basins that are all happening equal. These are pretty rare, but occasionally we do see them. A progradational sequence, again, goes from 1, 2, 3, and 4. You can see our shore face is moving seaward. So in this case, we have successfully younger parasequences deposited farther basinward. And this happens when you have a rate of deposition that is greater than the rate of accommodation. In other words, you're filling in your basin. A prograding delta does this. You have more sediment coming in, and you're filling that basin faster than you can subside it or grow it eustatically. And we have what's called a forced regression. In this case, accommodation space is going to be reduced, and the shoreline moves seaward. And this is what we also get what's called degradational stacking. So everything goes lower down. It's not just prograding out where your prograding deltas or prograding stacks stay at a pretty uniform level. This goes down. So this is truly lowering of sea level as we're dumping more sediment in there too. So coastal plain sometimes gets totally bypassed. And then you have sediment that's deposited in a far seaward position. So again, we can see some, if this happens to an extreme, this can also violate Walter's law. So here we can look at all four of them: retrogradational, progradational, forced regression or degradational, and then aggregational. So notice with the progradation, from 1 to 2 to 3 to 4, we're still kind of stacking up but out, and degradational, we're stacking down and out. And retrogradational is moving landward, aggregational just moves up. So those are our four parasequence sets. We've talked about what is a stratigraphic system, what is a parasequence, what are parasequence sets. Now let's look at system tracks. This is when we combine it all together. A system track is a depositional sequence that is going to, remember, be recording a full cycle of relative sea level rise and fall, and actually kind of rise again. Okay. Each of those stages of rising and falling and the substages within can produce predictable system tracks and erosional surfaces. And these are really the kind of the steel girders that make up stratigraphic sequences, are the system tracks. They're made up of parasequences. They're made up of erosional surfaces. Okay. So a system track will include packages of depositional systems that all exist at the same time, like a coastal plain, a continental shelf, or a submarine fan. And we have four of these: a falling stage system track, a high stand system track, a transgressive system track, and a low stand. In between each one, you're going to have surfaces. So the image that you see on the right is like the order in which you'll see them stacked. Underneath a low stand system track, you're going to have a sequence boundary. In other words, subaerial unconformity. You have your low stand system track, and then above that you have a transgressive surface. This, in other words, is the maximum regression. And then it starts to go up. Sea level goes up when we develop our transgressive system track. And then we have our maximum flooding surface. This is the all-time high. And that's when we start developing our high stand system tracks. These are all the sediments that are deposited during the high stand. And then as things start to fall, we have our basal surface of forced regression, a falling stage system track, and then we cap it with another sequence boundary, and we start the entire thing all over again. Let's look at the high stand system track. This is going to be made up of aggregational and progradational parasequence sets. They sit on top of a maximum flooding surface, and they're going to be overlain by the next sequence boundary. So this is happening. These system tracks are representing the sediments that are deposited during the highest of sea levels as they start to fall. So you have your coastal plains, your shallow marine sandstones, your offshore muds. So during this system track, the rate of sea level rise is going to slow down. And relative sea level eventually begins to fall, and you start going into the next sequence boundary. On top of the high stand system track, we have our falling stage system track. And if you notice the diagram in the upper right corner, that's when we're now starting to see things really fall. So the high stand goes from high to beginning of falling, and then this is all the sediments that are depositing as sea level is going down. And notice what we see is a degradational parasequence set of forced regression. So it goes from the high stand position and falls to a forced regression, the way we have that outboard lowering stacking of degradational parasequence sets. In this case, we don't have the coastal plains. We're bypassing those, and instead we deposit shallow marine sands and offshore muds and the various parasequences within them. Notice on top where we would have our coastal plain, we have a subaerial unconformity. We have exposure. Then we get to our low stand system track. we start to develop a new coastal plain, a smaller series of shallow marine sands, and a smaller series of offshore muds. These form as relative sea level fall has fallen to its minimum, and now it's starting to rise again. This is the beginning of a new relative rise in sea level, and we actually are starting to see a small amount of accommodation space because now we're starting to raise sea level again. We have more places to put sediments. And notice, especially on your coastal plain, you're depositing those right on top of your previous subaerial unconformity that happened after the falling stage. So low stand is from the low building back up. We then have our transgressive system tracks, and this is retrogradational. The parasequence set's moving in the landward direction. We've seen a shift now where we went from high stand to falling to low, and now we're moving everything back landward again. This is sea level going towards its high point in the landward direction. At this point, what we're seeing is the accommodation space is greater than the rate of sediment supply. So we're moving sediments in the landward direction. These types of system tracks also include transgressive surfaces, in which you have marine sediments overlying non-marine sediments. Notice where our offshore mudstones are in relation to the coastal plain sediments from our low stand system track underneath. So let's review the entire sequence again. We start out with a high stand system track. Remember, this is where things are at their highest and starting to fall. We shift outboard with a degradational falling stage system track. As we start hitting our lowest point, we also now have a subaerial unconformity. We start to build up a little bit with our low stand system track, the sediments deposited during the low and building their way up to the high. And then we push everything in a transgressive system track. Now we're in landward again. When the sea level starts getting to its maximum with this transgressive system track, that rate of sedimentation again is going to exceed or be greater than the rate of sea level rise. When that starts to happen, we see the aggradational process once again, and we prograde out with a new high stand system track beginning again. So there's our other high stand, falling stage, and we start the entire thing over. Not all system tracks are going to be present at any given location, obviously. You're not going to see a low stand in every single location. But you can see also we have subaerial unconformities. Those are what are binding those. So notice, in between our two red lines, we have a low stand, a transgression, a high, and a falling. We have all four. That is one depositional sequence in between those two red lines. So here's another review to kind of look at the high stand system tracks and what kind of parasequences. The geometry of the parasequence sets is very important. That's one of the ways of identifying these. Now, the boundaries that we have between our sequences can be quite a bit different, though. Sequence boundaries are those significant erosional unconformities and correlative conformities that we saw before. So these are going to be the result of that fall in sea level that erodes away some of the subaerially exposed sediment that we had deposited in earlier sequences. So those red lines again. These are diachronous because they cross time boundaries. You can have unconformities that consist for long periods of time in one place and not elsewhere. They usually cap the previous high stand system track. And what we're seeing with that erosional surface and the downstepping of sediments during one forced regression to the next associated with sea level is you're seeing these unconformities in between. So think back to those red lines we were looking at in the animation, how those are the unconformities that are binding our individual sequences. The sequence boundaries, those unconformities, can vary. There's a couple of different types. A type 1 sequence boundary is an unconformity, but it has what we call stream rejuvenation and fluvial incision. There will be sediments bypassing onto the shelf, and usually a really abrupt shift of facies basinward and some coastal onlap. Well, what does that even mean? Let's look at an example. These are interpreted, by the way, to form when we have eustatic sea level falling at a faster rate than the basin can actually subside as it's getting packed with sediments. Okay, so you get a relative fall in sea level at these positions. But let's take a look at an image of a type 1 sequence boundary. Okay, in this case, our unconformities are the dark lines, right? They're sitting on top of our high stand system tracks. With a type 1 sequence boundary, you have lowered sea level to a point where you can actually get fluvial or estuarial sandstones cutting down into these incised valleys right on top of your high stand system tracks. And you also get those transgressive surfaces further out. Now, what about a type 2? A type 2 sequence boundary, very similar to type 1 in all regards, except the extent of that sequence binding unconformity into the marine setting. So these two sequence boundaries also differ not only in the name of the system track lying above them, but also below. So let's take a look at this one. Notice we don't have that fluvial or estuarian deposit. And notice how our sequence boundary continues much further into that marine realm because we've had such a significant unconformity. So let's look at these two side by side and compare them together. So with a side-by-side comparison, this is the same text from the previous slides, but I just want to show them directly. Notice that with a type 1, you have that fluvial and estuary stream rejuvenation, so that's important to note. You also have submarine fans and levee channel sandstones that you don't see in type 2. And also, just keep in mind, this is going to happen when that eustatic level of fall of sea level, the amount of water in the oceans, falls at a rate faster than basin subsidence. A type 2, again, very similar to type 1, but in this case, our unconformity, do you see how that sequence boundary goes downward rather than outward? So we have our, and also notice the differences in what type of system tracks we have. Okay, we have the shallow marine system track on top of our high stand, while in a type 1, it's a low stand. Okay, so if you see fluvial estuaries or those kind of things, you know you're looking at a type 1 system boundary. But if you're looking at the upper boundary, you may not even notice it. So in the diagram that we have for type 1, our lower unconformity is a type 1 system boundary. But the system boundary that you see above that is the same as what we're seeing over at the bottom for the sequence boundary in a type 2. So we looked at some Wheeler diagrams before when we discussed unconformities and hiatuses, and these are really no different. You can actually do the same kind of work looking at age and correlating time with different sequence boundaries and what's preserved versus what is not. So that's something to keep in mind. That is a thing we can do too. That these are all unconformity bound, so you're always going to be losing something with that erosional surface. So we're going to go ahead and stop there. Remember that for lab, we are going to be working on what we call Lab Project 4, which deals with some seismic stratigraphy work. And also remember that lab project 3 is due. So I look forward to seeing everybody in lab before spring break. Thanks.